For millions of years, dinosaurs reigned supreme over Earth, towering and formidable. These colossal creatures, unmatched in their era, thrived in a world that was exclusively their own. Yet, their dominion met an abrupt and catastrophic end. Shrouded in mystery for eons, the demise of these giants has been a puzzle captivating scientists and enthusiasts alike. Now, with the advent of groundbreaking technology, the veil is finally lifting. Researchers have unearthed secrets long buried, the true origins of the asteroid that nearly eradicated all life on Earth. In the vastness of space, a celestial harbinger of doom silently traversed the cosmos. Known as the Chixulub asteroid, this massive entity bore the weight of over 1 trillion tons, a colossal force unfathomable to the living world. Spanning a staggering 10 kilometers in diameter, it was an embodiment of cosmic fury. Cloaked in the darkness of the universe, it journeyed relentlessly towards Earth. Its composition, a mysterious amalgamation of minerals and metals, held secrets of its origin in the distant asteroid belt. This time-worn ancient traveler was destined to unleash an unparalleled cataclysm, forever altering the course of life on our planet. For decades, the Chixulub impact event, which heralded the end of the dinosaurs, remained a partially solved mystery. Recently, however, scientists have managed to assemble the intricate puzzle of Earth's immediate post-impact environment. This breakthrough was achieved through a combination of advanced technologies: geological surveys, sediment analysis, and computer modeling. Key to these discoveries were core samples from the Chixulub crater itself, revealing layers of rock and sediment that captured the event's immediate impact on the planet's geology. Additionally, studies of fossilized remains offered insights into the rapid extinction patterns. Several significant reports have been published in scientific journals detailing these findings. These reports illustrate how the impact triggered a rapid, drastic climate change, leading to the mass extinction of 75% of Earth's species. The event was colossal. As the asteroid approached Earth, the dinosaurs would have first noticed an unusual point of light in the sky, akin to a star but brighter and growing steadily each night. This celestial body, initially a mere speck, soon swelled to a size larger than the brightness of the moon, casting a foreboding shadow over the ancient landscapes. As it breached Earth's atmosphere, the asteroid transformed into a fiery inferno, a sight comparable to a second sun descending upon the world. Its entry, marked by a deafening roar and a brilliant, blinding light, would have been like witnessing a cataclysmic firestorm. The sky, ablaze with an eerie, unnatural glow, turned day into a scorching dusk. As the asteroid neared its catastrophic collision, the intense heat and shockwaves would have felt like standing at the epicenter of a volcanic eruption. The immediate vicinity would have experienced a sudden, searing heat wave, causing widespread panic and disarray. As it penetrated the atmosphere, its speed, estimated at about 20 kilometers per second, caused immense friction with the air. This friction heated the asteroid to extreme temperatures, making it glow fiercely, like a massive meteor streaking across the sky. The asteroid, composed of rock and metal, began to partially melt and vaporize due to the intense heat, leaving a trail of glowing particles and gases in its wake. The atmosphere around the asteroid became superheated, forming a shockwave that radiated outwards at a speed faster than the speed of sound. This shockwave generated powerful winds and triggered immense air pressure changes. In fact, the atmospheric pressure increased so dramatically in front of it, creating a massive compression wave. This wave would have been powerful enough to flatten forests and cause severe tsunamis even before the asteroid made contact with the Earth's surface. The impact itself would have penetrated deep into the Earth's crust, creating a crater over 150 kilometers in diameter and about 20 kilometers deep. The collision, releasing energy equivalent to billions of atomic bombs, fractured the Earth's surface, causing massive chunks of rock and earth to be hurled upwards and outwards. This violent upheaval resulted in debris being ejected both horizontally and vertically, with some fragments reaching the stratosphere. The material expelled horizontally traveled at speeds exceeding the speed of sound, spreading across thousands of kilometers. Vertically ejected debris formed a towering plume, later settling around the globe as a layer of sediment. The sound of the impact would have been deafening, akin to a colossal thunderclap heard for thousands of miles. Seismic waves radiated from the epicenter, triggering earthquakes and volcanic eruptions worldwide. The asteroid's plunge into the shallow seas of the Yucatan Peninsula generated mega tsunamis, with waves estimated to be over 100 meters high, devastating coastlines far from the impact site. This would have left a crater peak, a circular ring formation of elevated ridges within a large impact crater, formed by the collapse and rebound of the crater floor following a high-energy impact. This ring, approximately 90 kilometers in diameter, consists of uplifted, fractured rocks, providing crucial insights into the immense forces involved in the asteroid's Earth-shattering collision. Let's take a look at the sequence of events that would have unfolded during the first minutes to an hour after the impact. By the way, are you enjoying this video? Do us a favor and hit the like button there. Also, make sure you subscribe and tap the bell icon so you never miss any of our brilliant content. You're officially an explorer now. At the time of impact, the asteroid released energy equivalent to approximately 100 teratons of TNT. This impact generated temperatures exceeding 10,000 degrees Celsius, instantly vaporizing the asteroid and a significant portion of the Earth's crust. A few seconds later, a crater, initially 30 kilometers deep and 100 kilometers wide, began to form. The Earth's crust, under the immense force, first compressed and then rebounded, creating a peak ring inside the crater, eventually measuring 150 kilometers wide and 20 kilometers deep. In less than a minute, massive amounts of earth, rock, and water were ejected at high velocities through the atmosphere. The debris was thrown upwards and outwards, with some fragments reaching escape velocity, possibly reaching the moon and sun, while others took suborbital trajectories. This ejection spread billions of tons of material across continents and into the stratosphere. Within minutes, seismic waves, equivalent to a magnitude 10 to 12 earthquake, propagated globally, triggering volcanic activities and fault movements far from the impact site. A supersonic blast wave radiated out from the impact site. The shock wave flattened forests and annihilated life within a vast radius, with air pressure changes and winds comparable to the most powerful tornadoes would have erupted globally. The intense heat and fiery debris returning from the atmosphere ignited global firestorms. These fires consumed vast areas of forest and grassland, releasing immense amounts of smoke and soot into the atmosphere and igniting materials hundreds of kilometers away. Also, mega tsunamis, with initial wave heights exceeding 100 meters, were generated, devastating coastlines worldwide with massive erosion and inundation. In less than 1 hour, sulfur-rich rocks vaporized by the impact combined with atmospheric water to produce sulfuric acid, leading to acid rain. This acid rain began to fall within an hour, contributing to environmental stress and acidification of surface waters. The spreading dust, soot, and aerosols then began to block sunlight, reducing solar radiation reaching the Earth's surface. This led to a rapid temperature drop in some regions, initiating a period of global cooling and darkness. The injection of particulate matter into the stratosphere caused drastic changes in atmospheric circulation patterns, affecting weather systems globally and leading to extreme weather conditions. The impact of the Chixulub asteroid set in motion a chain of events that would eventually lead to the mass extinction of 75% of Earth's species, marking the end of the Dinosaurs era. The scale and speed of these events highlight the fragility of life in the face of cosmic forces. a profound reminder of the dynamic and sometimes volatile nature of our planet. The tracing of this asteroid, responsible for the extinction of the dinosaurs, a landmark in paleontological research, was a collaborative effort led by an international team of scientists. The findings were groundbreaking. The crater, today found in Mexico, measuring about 150 kilometers in diameter, was conclusively linked to the Cretaceous-Paleogene extinction event. Analysis of shocked quartz and other impact-related materials within the crater and global sediment layers tied the event to a massive asteroid impact approximately 66 million years ago. Alas, the asteroid was conclusively believed to have originated from the asteroid belt. Deadly asteroids large enough to pose a significant threat to Earth are relatively rare, typically occurring on timescales of millions of years. However, the unpredictable nature of space means it's only a matter of time before another such asteroid could come within range of our planet. Given this inevitability, ongoing astronomical surveillance and research are crucial to identify potential threats early and develop strategies to mitigate the risk of a catastrophic impact on our civilization. One notable example of an asteroid impact captured on video is the Chelyabinsk meteor event in Russia. On February 15, 2013, a meteor streaked across the sky over Chelyabinsk, Russia, and exploded, causing damage to buildings and shattering windows. This event resulted in injuries to over 1,000 people. The meteor's entry and explosion were captured by dashboard cameras, providing incredible footage of the event as it unfolded. Another recent asteroid impact is that of asteroid 2022 EB5. This small asteroid, about 6.5 feet or 2 meters wide, was discovered only 2 hours before it impacted Earth's atmosphere on March 11, 2022. It hit the atmosphere over the Norwegian Sea, disintegrating before reaching the surface. The event was precisely predicted by astronomers, determining the exact location and time of the impact near Jan Mayen, a Norwegian island. Although too small to pose a hazard to Earth, this event was significant, as it was one of the few times an asteroid has been observed before impacting the atmosphere. The worrying thing is that many times they cannot be traced until impact is imminent. In December 2021, NASA's Jet Propulsion Laboratory used the Deep Space Network's Goldstone antenna to capture detailed radar images of asteroid 4660 Nereus during its close approach to Earth, about 2.5 million miles away. This event marked the most detailed observation of Nereus, a 1,100-foot wide near-Earth asteroid, since its discovery in 1982. The high-resolution imaging revealed Nereus's unique surface features, enhancing our understanding of its shape, rotation, and orbital path. Nereus belongs to the rare E-type asteroid family, known for unusual radar scattering properties and high optical brightness, reflecting up to 50% of sunlight. These characteristics suggest E-type asteroids like Nereus might be sources of rare or bright meteorites. The 2021 approach provided the best opportunity for detailed observation until 2060, when Nereus will be visible even through small telescopes or powerful binoculars coming within 750,000 miles of Earth. As of now, humanity lacks a fully developed and tested method to defend against a truly threatening asteroid. The NASA Double Asteroid Redirection Test, also known as the DART project, is a significant step towards developing such a defense mechanism by impacting an asteroid to deflect its trajectory. DART, which weighed 610 kilograms and traveled at approximately 22,530 kilometers per hour, successfully impacted the asteroid moonlet Dimorphos in September 2022. The impact altered Dimorphos's orbital period around its parent asteroid, Didymos, by about 33 minutes, a change which was later observed to increase to 34 minutes. This mission's significance lies in its demonstration of a kinetic impact technique as a planetary defense strategy, where a spacecraft intentionally collides with a potentially hazardous asteroid to alter its course. The successful alteration of Dimorphos's orbit provides crucial data for NASA and ESA to prepare for the possibility of redirecting an asteroid on a collision course with Earth. The impact ejected over 900,000 kilograms of debris into space, enough to fill 6 or 7 railroad cars, and displaced over 1 million kilograms of dusty rock. Like the video? Make sure you subscribe and click a thumbnail for more top content. See you soon, explorers.